angular momentum directed toward that north border there. The torque about the pivot point is directed toward the board, and that's the direction of the change in angular momentum. So that tells you the direction of precession. And so it's exactly the same principle as doing the classical.
Can you slide the weight out now? And
yeah, okay, that's the next thing you want to do. Instead, now if we have this weight overbalancing that of the wheel, then the precession goes the other direction because the torque's in the opposite direction. If you reverse the direction of the torque, you're going to reverse the DL.
And you get the velocity of precession depending on the distance to the axis, right?
That's right.
You can show that.
Of course.
Do you go to the Earth here? I mean, to talk about Earth precession?
I don't do this part D in that case, where it's just balanced, just right, we're getting precession.
From the perspective here on an observer, you know what it would be good? Is to paint some different color stripes on the edge of the wheel because it doesn't, I don't see it's moving.
I see what you mean. You just have to equal lever arms there and equal weight, so no surprise if they're balanced. If I move this one out to here, then of course that's a bigger torque, so it's unbalanced. And then if I move this one out here, and again now I have equal lever arms, equal torque, so it's balanced. So you have to wonder, well, what if I move this one on out here? Does that make them unequal again?
that's a good point.
And so I've seen rather complicated analysis, and you don't want to fall into that trap of trying to really and truly get from a mathematical analysis. The heart of the matter is you got two pivot points instead of one. And so the easy way of picturing things isn't that. It's just out of interest. And the question is, really, I think it's excellent. The question is, when I pull on this, will this spool come toward me, or will it move away from me? Then you got to be wondering the answer to that. And then show how it comes toward you, unless you make the angle big enough, then it moves away. And then they're just at optimal angles with no rolling at all, but sliding, which the line of action of the force goes right through the point of contact.
That takes years of practice, right? It's like Smallest Brothers.
No, you'll catch on very well.
Yeah.
But in case it doesn't, it is true that one out of 3 or 4 times it doesn't.
Are there marks on that?
You don't have to have any marks because there's little indentions where it will go.
Okay, so there is an indentation.
To the end here and there's a...
So you can't miss. So the idea is, when you pull on this, it's better, I suppose, if you have some sticky something so it can stay in. And that's always annoying if it doesn't stay, but still they accept it.
Yeah, it bounced in, but
Yeah, they see it.
Oh, so it's just bouncing out?
Yeah, it bounces out.
is there in one of them there used to be like a foam pad or something, but
Maybe one more time. I usually find out half the time it works.
yeah,
It's kind of discouraging when it doesn't because it's not quite as tricky.
yeah. But,
Let me do it one more time. I don't know any particular technique to make it better. I can really say that it usually works more often than it doesn't.
Hey.
What do you use?
So the question is, if you race them down the inclined plane, which one will win the race?
So this is the can of beans and the...
Yeah, I would like this better, to tell you the truth, than the can of beans, but, you know, that each his own. All right, so the one that has the greater moment of inertia will be next to the class, and so you go to vote which they think will win the race. And then you have to go through a little theory, really energy study, about 3 or 4 equations long. Shows you why yellow wins the race. So let's see how these two do. When we race them, they look the same. And so let's try to get. Wow. Let's do that.
So that one's just off center? Just center
Yeah, it's got a
of
little metal strip off center on one side, and there's a little dot right here that shows you where it is.
So it's trying to lower the center of mass.
This is you give an exam and an answer without giving all the inputs.
And then this has salt on the inside. The salt is just, that will accelerate with the salt continuously. Back and forth.
See if I can do it.
We'll set on top and extend just a little bit more. And then that one, extend just a little bit more yet. And circle. Gradually we're getting more and more of the mass out beyond the edge of the counter. And so the question now is asked, on this next one I'm going to place it such that the center of mass is beyond the counter. Or get things out of the way. So that, and then you take a vote, you know, do you think that this is going to topple over, or do you think it's going to stay in equilibrium? And usually they vote that it'll stay. All right. Now, this one I'm going to have the entire block beyond the edge of the counter. The question is, will it cause things to topple over? Get a vote. After your vote, well then you and now this, they've done the homework probably, then they really appreciate it. Usually they would not have done it. But this is, let L be the length of the board. This is L over 2. And this is L over 4. L over 6. L over 8, L over 10, L over 12, L over 14. That's the optimal situation where everything is on the verge of toppling over.
So you have margins or something?
Oh, now I'm going to show you.
So, sorry, the ratios are 2, 4.
Yeah.
What?
2, L over 2, L over 4, L over 6, and so on.
Uh-huh.
You talk about Roman architecture out of here, because that's a classical Roman art, right?
First thing is worth doing. Oh, I didn't bring a pencil. Anybody happen to have a pencil with an eraser on the end?
Chalk on that?
Anyway,
What does it do?
I'm going to let you be my... You can see where I've done it. You'll be my student.
All right, sir.
And the idea is, you can't rush either because you want them to take their time and get it real steady. And anyway, all I ask the student to do is just pinch it. When you think everything is nice and steady, just pinch it.
Oh, I see.
Oh,
Now let's do it again.
Sorry for that.
it's an old sewing technique.
Yeah.
Let's do it again. Two really is enough, but I like to go ahead and show them to get the same intersection of the third one. Okay, well, we did just a real clear cut. All right, now, if we've done things properly, that should give us a center of mass, so let's give it the acid test here. Ta-da! Ooh.
Very good.
Mm-hmm.
That's a nice and simple.
Mm-hmm.
You lower it a little further. And so now, I've got another demonstration I didn't bring with me where I demonstrate this from going to one side or the other, the depth separation. But this the same deal. You wonder if it'll fall off to the side or also will it fall forward or backward. You really wonder.
Right. Is that here? I mean,
I keep it in the cabinet. My wife made this for me. Mainly the brass one. Anyway, it's that principle.
it's stable enough.
Okay, hold on. How
To
do,
get your shoulders forward, you find you just cannot get up on your toes. You can't do it because you're trying to get your center of mass inside the wall when you do that. You just can't do it. Same thing.
So you got this one where you try to touch your toes. And then this one where you try to lift your foot.
That's a simple one.
okay.
Just hit the red button with your
The question is to explain what they observe.
Now, by power of mind, unbend the spoon.
Odd shape here, and if I try to support it on one end of my finger, I just won't hold. I don't care how I try, it just will not hold. But if I put my belt in there, there's absolutely no problem. And of course, you're throwing the center of mass of the belt and wood below the point of support. So that's the big point that you're stressing. The center of mass has got to be below the point of support. Stick like this on the end of your finger. Well, you can do it, but it's really not easy. Whereas, if you get a long stick, then you find it's just the easiest path. Just nothing to it. So this is the principle of why clowns are on stilts and circus. Why does that length give you so much more stability? That's the question. Well, it's the same analysis of you have a stick that length L. The torque is mg/L/2 times the cosine of this angle. see, that's not focusing. And, see, what I really wanted to say though, that torque, here's the interesting. The torque is the moment of inertia times the angular acceleration. And the moment of inertia is 1/3 ml squared. And so, the whole point is, the mass is going to cancel. You can see, comparing left and right-hand sides there, here's the point. The angular acceleration is proportional to 1/L. That's the key argument. And so, the longer the stick, the smaller the angular acceleration. And therefore, you have time to adjust. If it starts to fall, because the angular acceleration is small, you have time to adjust and get it back where it's stable. Now let me give it a try. This one, fixed emotions about this demonstration. I have to have a lot of patience. But anyway, you just start. You began this demonstration with the explanation that when you exert a torque, there are two things that can happen. Either you can have change in the moment of inertia, or you can have acceleration. So when we exert a torque, first of all we see that it starts rotating. But we also see, as we continue to exert more torque, that the loop is spreading out. The distance from the axis is getting greater, so the moment of inertia is increasing. So as you continue doing this, anyway, you finally get your lariat. I always wanted to be a cowboy. Anyway, that's the principle of the lariat. You balance in these two cups of water. All right, now the question is, all right, if I insert my finger in this cup of water very slowly, then water will rise around my finger. And if I do it ever so slowly, will that have an impact on the balance? That's the question. Will my inserting my finger have an impact? So yes, it does. Now, Now, you know from Archimedes, there's a buoyant force that exerted corresponds to the way the liquid displays. So there's a buoyant force on my finger. But then according to Newton's third law, there's a reaction force from my finger onto the water. And then using Pascal's principle, that's transmitted to the bottom, and then that adds to your retardant. So there's a lot of fluid physics in that demonstration.
It's more than that, it's also a reduction of the pressure because the air surface gets reduced.
You're adding to the pressure by inserting the finger. In effect, because of the reaction, more pressure, more force transmitted to the bottom. All right, this is a demonstration of Bernoulli's principle. And you're obliged to explain why the ball stays in the jet stream. And it's because it tries to fall out of the jet stream. But as it tries to leave the jet stream, then the air passes faster over the top than on the bottom, and the pressure is less, and the velocity is greater.
Did you try how big an angle you can have?
That's about it.
How do you start it? Can you show again? Okay, I missed that. I mean, if you take the ball away and try to put it back in. Just like that.
It's no problem. It's easy. Of course, they want to know how far you can go without like although is able to support it. Anyway, first of all, you explain how you get your different steady waves. All right, and then explain how, of course, it's the air passing by the outer end at a greater velocity that causes the pressure to be less, and in effect, the air is sucked through as you swing it. And then as the air passes through, if you do this with a pipe that doesn't have these corrugations, it won't produce steady water. Somehow or other, the interaction with air passing through the corrugations produces sound, and then the sound collects it into the tube. All right, so it's for sure, it's Bernoulli's principle that's behind it all. So to add to that, anyway, there's one more thing you do. Oh, where's my ball? Oh, lights. Anyway, it's more effective to get a big pile of paper.
They have that confetti down at the coffee shop. We'll have to color confetti.
Somebody used to pick that up.
You're right. Make a terrible mess.
Yeah, I know. I always do it because the janitors will get mad. If you haven't seen the Cartesian diver, here is one. It sits in there, and I can use it. All you got to do is squeeze, and it comes down. And you're supposed to Cartesian diver, it's called. And well, let's see. You squeeze, you increase the pressure, and cause that little balloon to collapse, so that it's not displacing as much water, and therefore the buoyant force on it will be less, and then therefore it sinks. If it's right, the balloon has to be just barely supported enough to float, so that when you cause that balloon to collapse, then the buoyant force is not sufficient to cause it to float, so it goes from the bottom.
How did you get that to balance?
what it's trial and error.
Yeah. That's, that looks like another one of those multi-hour,
What's the connection to Cartesian?
That's a good question. Because we talked about Cartesian coordinate system.
Right.
I don't know the answer. This one's kind of fun. It's a hand boiler. You haven't seen one before. Methyl chloride in there. And so you show the class how if you give it the warmth of your hand, it causes it to boil, apparently. And the truth is that it's a fraud. It's not really boiling at all. And what happens, though, the warmth of your hand, the vapor pressure is such just above that methyl chloride. And when you do give it the warmth of your hand, that pressure down here above pushes down. The vapor pressure increases and forces it up into that little tube. But you run out of liquid, and that's what causes the bubbling. It just looks like it's warm.
Nice question. I don't want to sing.
Now, if you haven't seen, when you go to talk about one-dimensional collisions, a real good example is a M and 3M mass ratio, where your incident particle has mass M and target mass 3M, and you find when you solve that they move apart with equal velocities. Proposed conservation of momentum and energy. And you find that the theory, you want to do the theory first before you do this, because you present the result of the two velocities after the collision will be equal in magnitude, opposite directions. That's what you show. And so then, this apparatus has that 3-to-1 mass ratio. So, it's an elastic collision approximately. So you see them going apart with equal velocity after that first collision. Of course, it comes back to where it was. If you had time, I never really have time anymore, to do the second collision. That's really interesting. And show that this target is going to be at rest after the second collision. And anyway, the combination of two collisions is a nice point. Just that takes a lecture to do the whole thing.
Do we have several of those in the chain?
There is another one there.
Yeah.
Sure is. Okay, if you haven't seen this before. Give a little angular momentum there, and it causes that vortex to form. And so we want to discuss why you can't have water flowing right in the dead center. Water just will not flow dead center when it's got any kind of angular momentum. And basically, because your centrifugal force on any chunk of water you want to consider is the mass of that chunk times v squared over r. Now, it gains velocity as it, because of due to gravity, is falling. But on any little chunk of water you want to consider, you cannot have a zero denominator because you don't have that much force pushing in it. And it's just not possible to satisfy your equation with a zero radius. So that's why you get that vortex. Use that other rod. Can't see. It had markings on here.
Very sensitive.
Yeah, there, but it's up in here. Up where I left it, you barely can see. Well, let me give it a try. Anyway, if you hold the rod like this, you get a certain frequency, and actually the wavelength's twice the length of the rod. And if you touch it anywhere else, it shuts it down. Because you've got this one node, and that's the fundamental mode of vibration. And then if you hold it to 3/4 tone, do it again, you get the next harmonic. Only this time, notice, you can also touch it down there. You've got 2 nodes instead of 1. Got 2 nodes. And if you touch it somewhere else, it shuts it down. All right, now it's happening, but I don't seem to have this other rod. Yeah, maybe this will get it. All right, this is at the 5/6 point. Shorter wavelength still. Now this time, I've got a node in the middle as well. And now this is what I need it marked there. I don't have it marked down there. I don't know. It's got 3 nodes and I don't have it marked down there. And the other rod is kind of better because it's marked more clearly.
Are you excited?
You just hold it and stroke it.
You use your fingers?
Thumb and finger. Thank you.
That.
Same way I kick this. I'm holding those 2 notes. It's that second harmonic. Same wavelength, 2 nodes. Why don't we hear it? Well, the explanation is that's a transverse wave. And the frequency is very low for that transverse wave. What we were hearing a while ago is a longitudinal standing wave. And velocity of propagation is much greater than longitudinal wave. And that causes the frequency to be much greater so we could hear it. That's that dry. So this will last you for hours. Oh, there's something I need to get. Darn it.
What is it?
Well, let me go to my office or room. And, now this is just an empty test tube. Just an empty test tube, nothing in it. And I want to put this apple in here. And I've got this flexible tube. Class, this is 77 Kelvin. That's really getting down there. And first of all, let's look at the balloon. Let's see what happens to our balloon here. You just talked about the ideal gas law, so that you know relationship of volume, temperature, pressure. So nobody's surprised if it collapses in the balloon. But you can tell me, you don't want to. You got to be careful. You can sure lose fingers here if you get it too cold. You see the air, the liquid air in there, sloshing around. See the air liquefied? And then let's see what's happened to our apple here.
You don't get burned.
And then you take a look at your flexible tubing. Everybody squint your eyes. Everybody, squint your eyes. Squint your eyes. What is all over the room? So anyway, you're impressed, you know, with the temperature because of the good ones. And then you pull out your test tube. And look what we've now got in our test tube. In the bottom. Liquid air. So, done that. So, appropriate time to ask anybody if they'd like to take a sweet. Would you like to have a little drink?
No, I just want to watch you paint.
All right. Is there anybody crazy enough in this room to drink this stuff? All right, it's a hazardous profession. And you always throw a little.
What does it really do to when you put it in your arms?
Well, it evaporates so fast.
You don't get burned?
You don't get burned. It just evaporates so fast. We have here two tune bars, both 256 hertz. They sound the same, but if you were to screw this little thing, one about positioned out right there, and do it again, it's hardly any difference. But I didn't try hard, but I found a note what I did. So now, let's do it again where you are off note, more like that. Now you have two superimposed frequencies, slightly different frequencies, so you hear the beat. Beat frequency is the difference in the two superimposed. And then you keep making the difference greater with the beat frequency going up. The more you greater the difference in your two frequencies superimposed, the greater your beat frequency. That's what you're showing. Let me just... does have to do by adjustment on that. The acid in fruits as well. So what I've got here is I've got a copper electrode and a zinc electrode. And you see how it produces enough electricity to begin the clock. This is called my tutti frutti clock. and so it starts out at 1 o'clock, and you know, keep lecturing. They'll see the time change to 1 after 1, 2 after 1. You know, just a clock. And so you have a completed circuit, and those two apples comprise a rotate cell. And you explain how well copper and zinc go into solution with different tendencies, and that gives rise to a potential difference across the spectrum.
Is that your personal?
As well?
Potatoes, get a matter of fact.
About grapefruit.
Bananas and potatoes.
Is that your
Yeah,
personal?
oranges.
Is that your personal also?
Yeah.
Okay, we should.
Personal apples.
That's it.
A brief discussion of what inertia is. So you come to the statement, the bodies at rest tend to remain at rest.
We use wine.
It's much better if you do.
Probably helps if take a few sips before you.
No, it's much more effective if you do.
I want to get a candle too. Light a candle and do the whole-
All right, so anyway, you're supposed to understand that bodies at rest tend to remain at rest. Such a good American. You got to practice a little bit ahead of time.
With how many sets of dishes did it take to?
All right, here we go.
Yeah.
Oh, you always get applause.
Which way did you pull it? Pull it straight out? Or
Straight out.
Pull it down.
But don't do this.
Yeah.
Don't do this.
You wanna go
You
down.
start where you are and then pull down.
Uh-huh. We need to get some fabric
Yeah,
like that.
I
That's
talked to him about where he got that.
yeah. That's
This is too. So you
that's-
gotta have
Is that
special
something
dishes
which
really.
is
You gotta be sure they're not
Yeah.
stoneware and rough on
Right.
the bottom.
uh-huh.
And like I said, I wanna get us a candle holder and a nice candle.
I'm supposed to start volume and the frequency.
So that is it?
Trying to get a standing wave here. Let me go up to a higher frequency.
That's one.
Cool.
Can you connect it to some Brahms sonata or something like that?
Well, you take a meter stick and distance between two crests is going to be your wavelength. You read off the frequency and you can calculate them to the class the velocity of sound. Can everybody see the oscillation of that little spot? I had it a little bit better. You can see it just
Which wobbles?
wobbles just a little bit.
Yeah.
Well, depending on how you get it perched on here. What I've got is a old-fashioned pocket watch with a little tiny mirror set in some tacky wax. And you know, the laser beam is reflecting off that little tiny mirror. And if you're as close as I am, you can really see the oscillation very clearly. And anyway, it's conservation of angular momentum that you're demonstrating, because the flywheel on the inside of the watch works. It was going this way and this way. So the watch as a whole has to go in the opposite direction in order to conserve angular momentum. So the oscillation, anyway, it's a demonstration. The conservation of angular momentum. The flywheel going one way, the watch as a whole going the other.
How do
And that's just a crystal on top?
It's a little tiny mirror.
Mirror.
A little tiny mirror that's embedded in a little bit of tacky wax that I put on. I inherited that watch some many years ago from my father. Much younger than I, but when I was young, let me just tell you about this song. In 1927, Hoagie Carmichael was a homecoming weekend. He had just graduated from law school, and he was visiting the campus at the University of Indiana, where he had done his undergraduate work. And it was a starlit sky, and he was inspired at this melody. He was an attorney, but this was the musical aspiration for his life. And anyway, this melody just came to him. And he went back to the commons area where there was a piano, and he worked it out. And his roommate was old roommate there that weekend too. He liked it, hearing how he was inspired. It was his roommate that named it Stardust. Well, anyway, he had a sort of ragtime beat, and it was Herbert Young, a Hollywood producer, that slowed it down, and he hired Mitchell Parrish, who had done the songs for a number of movies during that period, and to write the lyrics. Anyway, Mitchell Parrish wrote these lyrics, and it was published in the year I was born, 1929. And all through the 30s, this song grew in popularity. And in 1939, it was Artie Shaw, who you probably never heard of. It was artist where they produced the first gold record that was selling 1 million copies. And then about a year later, Frank Sinatra sold a different version, another gold record. And then a year after that, it was this one we're hearing, Nat King Cole had his first gold record. Stardust. All during those years, I was in junior high and high school, and we had lots of dances back in those days. Every weekend, there was some school dance or anything like that. Anyway, this was always the favorite, last dance of the week, Stardust. And in one other thing, in 1971, there was a survey made of songwriters all over the country that have been in this business all their lives. What was the most loved song of the century? And Stardust came in first. But right after that, suddenly nobody ever heard Stardust. Right after about 1970, it just faded. It's not in a musical. That's what hurts. Anyway, it came back 22 years later as the background for Sleepless in Seattle.
Dreaming of a song, a melody, heart's new remedy.
All right, well, what I want to do,
And I am once again.
now, the laser beam goes into the window of this photodetector, and there's a little amplifier in that detector and a speaker right there in the top. So the point is, it's laser transmission of sound, what you're doing. And it's a modulated laser beam. And this is a special laser that does that. Cut it off.
What's modulating the?
Well, that's all inside the laser. It's a specially designed amplitude modulated laser. What is? like the guitar box that gives you the volume that you need with the guitar, or like with a violin. If you had only that violin string, you wouldn't hear a blooming thing. It's needing that reverberation, the sound box, it's so important.
So this is when you're talking, do you talk about resonances in class as part of wave section?
The sound. Anyway, that helps to make it fun. But this is one that needs some kind of. Let me show you what I do. And what it's a little bit of a problem. By the way, I need to turn this laser over to somebody. It's about $1,000, and it's 10 milliwatts. And you need for these diffraction demonstration sort of powerful laser. It's neat. And I've always kept it in my office. And I just really think we've had too many things stolen from this demonstration. For example, the slide projector was stolen almost exactly a year ago. And well, I just hate to see you keep this in the demonstration. Anyway, the class has to come up close to see this. That's what's needed is 20 turns. Wire around it, and anyway, the wires themselves provide the axis for the rotation. They need to have a magnetic field, so anyway, I picked up these magnets that our teacher used. So anyway, the idea is to just connect to a battery.
That's why we need longer cables.
And it works. What's happening sometimes. I'm not able to keep going. Let's go back. Well, anyway, it's
Sounds like they're cut.
that's my Mac motor. Let me explain why it's having a little trouble. See, I don't have a commutator, and I've used it so many years. It's gotten
Insulation.
yeah. See, I took all the insulation off all the way around on one end, and on the other end, I took it off on half on, so that it's getting a current half the rotation, so it's getting a torque half the time, and no torque at all the other half. So it's always getting, theoretically, the torque in the same direction. That way you get around having to have a commutator. But my problem is that it keep wearing off, and it's more than just half on one of it. And the more you use it, it's kind of fouling it up. And I need to readjust my wire if I'm going to get that insulation. This is right here. Anyway, it's like a pendulum being suspended from the point of support there. The center of mass is maybe like a centimeter below the point of support, so that when you start oscillating, it's like a pendulum oscillating.
It's an inverted principle.
Anyway, it's another demonstration of that need for center of mass to be below the point of support. It flows very easily on that mercury, as you see. hardly submerged at all because the mercury is so dense. So it floats easily. And but then if I press it all the way down like this, so that it's sitting on the bottom, then there's no liquid on the bottom side and it doesn't float. It's demonstrating that need for a liquid on the bottom side. That's the difference.
That's a basic of the bridge gearbox, right?
What?
What the bridge gearbox.
Right. Sorry, it's still true. It generate speculation over why this top, sort of mystery top one keeps going. I've had to go for a weekend just to see how long it's sitting on my desk. You know, it keeps right on trucking. And you can just tell how the energy is first coming from, pull her leg. But anyway, I got a second one so that I can explain what's going on. This is an electric motor. And what you have there is a little bar magnet that is rotating rapidly. You know, when you have a motor, either the coils can rotate in a constant magnetic field, or you can have the coils fixed and the magnets can rotate. Some electric motors have the magnets, it's the magnetic field that rotates. Well here, that's what's happening here. You've got on the underside of that pedestal, you've got a fixed coil. The coil doesn't rotate. And there's a little bar magnet in this thing that is rotating. And there's a little transistor in the circuit, and a few years ago, Al Lundberg and I really got into figuring out what's going on. But there's a transistor that interrupts this circuit in such a way that it gets a kick each time it rotates. So that the rotation is always in the same direction. So what I want to do is just simply, briefly, just charge up the capacitor.
That's a whole Farad?
One, yes, right.
I don't think I've ever seen a whole Farad.
That's what's good about it.
They're not common.
I have kind of system with better end.
Okay, so I'm discharging the battery with a little light bulb. See? We talk about transient circuits, an RC circuit, and this shows the exponential decay of your transient circuit.
Right. This is a good one.
Yeah, it's simple, but yeah. No, I mean they can see the battery's not attached, so
That's
it's got to
right.
be.
The storage of energy is
Uh-huh.
in parallel place.
You can calculate the time constant and.
Yes, too, I've got this little generator. Show you the generator in action. Buddy to, for different points of the room, get your eye level either by hunkering down or by on your tiptoes. Or, you know, what I want you to do is have your eye level right at the top of the room. You know, that your eye level be the same as the top of the can. So keep watching now as I fill this can with water. All right, now you can see the very top, can't you?
Mm-hmm.
The light that now appears right at the surface.
Mm-hmm.
That light is actually at the bottom of the can. And it's the bending of the light rays, into your eyes that allows you to see that. I'm going to switch here. And it's embedded into some putty so that it's waterproof. So that's what that means.
The switch is
So
out.
we've got to be careful. This is not as sturdy as the one we had before. These Variacs, they've got a circuit breaker, a little foot, but anyway, you can't go full speed with this or you burn out the fuse. Anyway, let me set it about 20% there. Oh, good grief. Good thing. Checked this out yesterday, and I don't know why they vibrate.
I used to connect.
Good grief, this is on 0.
Some of the theorists are like the electrocuted cells.
Anyway, there's an obvious difference in, when the cooling down hits the ceiling and it makes an impact. But I wouldn't go past like 90% or 85% and do that.
There's enough resistance in the coil so it's not too bad to leave it on for a little bit.
You can change from here to brass, which has different resistivity, and you show a different height.
Yeah, let's see.
It's the same current, right?
Yeah.
Nothing changed.
Same current.
Yeah,
Something, getting something.
Yeah, this needs much higher value.
Pastor put in series with this coil. So that, let's see, I'm going to put this on about 60%. So that, that's a bit too, I mean, the word I'm going to bring from. Anyway, everybody, see if you can't see a little bit of attraction instead of repulsion. I need to go a little higher to get it.
Yeah.
See if that's out. I'll go up to 80%. Anyway, you can see a little bit of attraction.
What's the circuit?
Well,
There's the same coil.
an aluminum disc that is allowed to swing between the poles of a very powerful magnet. And you see there's a braking that takes place. This is called magnetic braking. It's very well known in the industry. You don't see the eddy currents produced, of course, but you've got electrons and atoms that have the velocity of the disk entering that magnetic field, and the Lorentz force exerted on those electrons causes them to move in circles. And the eddy currents produced then give rise to an I cross B reactive force. And that's where the braking comes in. And since they need a little convincing, you put in this other aluminum disc that has these little strips cut out that prevent the formation of currents because of the interruptions there. In this case, it's going to be free.
I mean, the current still flows. It's just that this loop is so much.
So that the slide projector can serve as a source of light. So
Oh, yeah.
oh, that's pretty.
Yeah,
Okay.
that's much better than,
Oh, that's good.
yeah.
I never succeeded in having the light source properly. This is a good thing.
Mhm.
Beautiful.
Sir.
I'm going to show you two little, these need to be repainted. These are just little sticks. One was painted red, one was painted blue. And I just want to show you how these look when you put them in the different colors there. First of all, the red looks red when it's in red light because it's the way the paint does it, reflects red. But notice how when you move into the yellow, it's immediately black. It appears black, yellow and green, because all the other colors are absorbed. Red paint means it reflects red, and that's all. And when I do a similar thing with the blue, the blue starts out black when it's in the red region, but notice this blue is not all that good a paint because it reflects green as well as blue. It looks black in the yellow and red region, but it's not a pure blue because it reflects both green and blue. Zero part makes the point. 12. I've got two opposite forces on two sides of this, pulling in opposite directions, giving me that reading. So that little one up interesting. Now what will let's observe under Newton's third law that in order to get a reading of 12 on one, you've also got to get a reading of 12 on the other as well. And again, is to be emphasized that on each of those spring scales, got two of them, you've got two opposite forces of the same magnitude giving you that reading.
Do you have something which shows
The prediction of what will happen now with this third scale. I put a third one out and do it all over again. You predict. I'm going to get a reading of 12, and you predict what will happen with that middle scale. Will it read 0? Will it read 12? Or will it read 24? And we get all kinds of predictions. But anyway, it's the same old story. Every one of them will give you a reading of 12. They're not well calibrated, but that never seems to be a problem. So this is, you see here the light from that laser beam passing through the Dr. Pepper bottle, and then it follows the stream as it exits. So that's total internal reflection, almost. It's not total because we see it, so some of the light's escaping. But for the most part, the light follows the path of the water because of that internal reflection of the surface of the water stream. As it internally reflects from the inner surface of that blue side. And anyway, you find out how this is called the piping of light, and this was the forerunner of fiber optics. It's used extensively in photography and medicine, where they use optical fiber to photograph internal organs. That's been around for a couple of decades. As part of the discussion of virtual images, everybody in class can see the candle. Well, you know, it's better not to turn out the lights completely. It's better to turn them down. About like that. All right. Anyway, everybody can see the candle apparently burning in a glass of water. And the discussion centers around whether or not you've got a real image or a virtual image. And of course, it's easy to understand how when you're just looking at the image of the candle burning, I mean, that's got to be virtual. Because the light is just reflecting from the glass panel into your eyes and giving you the appearance of having the rays appear to come from behind. But a little trickier question, it is the glass of water, is that virtual or is that real? And the inclination is to say, well, those rays really were back there where that glass of water is. So you might say, first blush, that is a real image, but not true, because when light passes through a parallel-sided glass block, it refracts twice and emerges parallel to the original direction. So even in the case of looking at the glass of water, there's a slight displacement that has taken place, so the image appears in a position where it wasn't. Well, it's not true. So both are virtual images. And it just serves to emphasize the meaning of the virtual image. And it's interesting to change that tension. Let's do it one more time with a lot less tension. Because then you get a real feel. See, I had trouble getting that fundamental when I have too much weight on it. Can't start out.
How much weight did you have on?
Well, right now I'm putting on 100 grams. I've got 200. Let's see if we can get at least the fundamental. Let's just try it. I don't. Another. There were two resonances. Now, you take off, make it open. Get one. That's the only one you get. Well.
Did you go out farther, or?
Beg pardon?
Did you go out farther than?
I didn't get my frequency. I'm just frequencies shows now the blue here. That's my problem. One. Oh, let's see, man. You have longer wavelengths with it closing.
Yeah, close only has odd harmonics, so.
That's right. So you.
Right. Wait, but is it?
Closing, and that's when you get the longer wavelength.
Yeah. Because the back end is effectively open, since it's.
Yeah, I believe so. It is because it's a vibrating speaker.
It's driving it from the node.
We've got a little speaker there.
Yeah.
So it's effectively, it's like an open end. Well, anyway, you can play around with the frequencies to get it like you want, but it makes a pretty convenient resonance. Now, I bet it's not going to work, but let me just show you. This is just a little piece of wrapping paper. I use some Scotch tape to make a loop on it. And these are rubber sponges. Rub an electron off on that paper. This is a golf tube. A golf club came in this tube. Sorry. It's just not there. Usually I can make it float around the room. And it's really good. It's just not going to work today. It's too humid.
I've noticed this tremendous effect of humidity. I brought from home my wife's amber jewelry to show the attraction to pieces of paper, and when it's raining or humid, you can't do that.
Wow.
North pole on this side, so the magnetic field toward the rear of the room. And so I had my current going this way, I crossed into D and up. So I'd like my current to go this way. So I'm going to up. So I'm coming out of the positive terminal here.
It's charged, okay.
You see the upper lip. I like to put a rheostat in series and cut down that current. It's just a little bit too much current. Better to cut it down, not have quite so much drama.
If you have a thicker cable, that's another reason to have a thicker cable. You don't spark so much.
I strongly recommend getting that rheostat in series and gradually increasing the current.
Yeah, I mean, this is one you can't leave it on, so that you can't levitate it too long.
So you want your negative terminal.
And the box itself is just a power supply, or what?
Yeah, that's what it is. Solid state induction coil. Puts out a very high voltage.
But it's a constant current, DC or AC?
It's DC.
DC. So it's DC current.
Okay, let me show you. Look at that. Boil it off this little plate right here, and go through that slit, and then we hit that little photosensitive screen. I got this turned way down. I got this a little bit. This thing puts out X-rays, and I've been told for years not to do it. So my answer to it has been to keep the voltage real low, so it minimizes the hazard. But anyway, we've got electrons going from the positive terminal, from the negative terminal toward the positive terminal. So they're going toward the door. So the velocity is toward the door. And now I'm going to superimpose a magnetic field. This is the north pole, that's the south. So the field is toward the door. So let's see now.
Current goes the other
Well,
way.
it's the Lorentz force, Q, V cross V. So the velocity is this way, V cross V, that would be downward, but then there are negative charges, so the force is going to be upward. So we should see an upward deflection by instead of that. There you see it. So now if we reverse the field, we will see a downward deflection. Perfect. So it's a good demonstration of the Lorentz force law. But you'd be surprised how much furor I caused one summer doing this demonstration. Because, the X-rays are coming from that, you know.
What's the
Well, the X-rays come even when this.
alcohol?
Yeah, just
and,
filling the little well there.
okay.
And you've got a little wick that soaks it up. And so you just light the fire. All right, now this, it's always more interesting if the thing works. I probably need to have it audited in 6 months. All right, so what this is all about is air is the working medium inside this little cylinder. It's just air heating up, and the air expands, pushes on a piston, which turns the flywheel. Notice this other piston's going in over here, that one's going out. So this, as the air expands, this one goes in and pushes a new supply of air into the cylinder, which is then heated, and the process is repeated. All right, now. That air conditioning always tends to. Always have the most trouble when that air conditioner's going. It'll really get up some speed most times. That's not good. All right. The advantages of a Stirling engine is that you can burn anything. You can burn wood or paper or whiskey or you name it. Just any fuel, can be used. And so air is your working medium. So it's called an external combustion engine instead of an internal combustion engine. Real carefully at those holes. See if you can see any difference whatsoever in those two boxes.
Is that the question?
So anyway, you open the black one first, and then you open the other one, it's white. And the point, it doesn't matter what the color is, that's the black body totally absorbing everything that enters, so it's going to appear black.
That's neat. Okay, that's a good one.
And for polarization, let me give you each a mirror. Let me go get these little Polaroid sheets. Kind of a problem. All right, what I want you to do first is to put your finger over one end, and you'll see an image. Let the light from above reflect. And I want you to get it where it's real clear now, where you see, first of all, you tell me what you see. When you look at your finger sticking up over one end, kind of rotate it around, tell me what you see that's kind of different. Just get one finger, and I want you to look at it. What do you see that's a little unusual about the image of your finger? It's double image. Change the orientation of the mirror till you see those two images very clearly. All right,
Yeah.
it's because of reflection from the front and the back surfaces of the mirror, of the glass. Okay, now,
There is a double image if you
trying
look
to
at the
use
small
at
angle.
about Brewster's angle, about 57 degrees angle of incidence. Rotate it until you eliminate one of those two images. You need to jiggle it, get your images where they're very clear, and then you rotate your, looking at it through the Polaroid sheet,
There are two images now,
you rotate your Polaroid
and you
until
can
you
rotate
eliminate
it out.
one of those two images.
Yeah.
One way you see in both of them, the other way you see them in one. And so it's in only one case, it's the one that's reflected from the front surface that's plain polarized. The one reflected from the back surface is not plain polarized. So you're wiping out of your Polaroid sheet the one reflected from the front surface. These are just film cartridges I got from a camera store. They're always going on. And all right, here's everybody. Please follow my directions. First of all, we're going to be looking at the light fixture above, and I want you to discover there's a hole in the rear, and it's from the rear that I want you to look. And so for this first little exercise, I want you to do a little target shooting, and everybody have your pin head up, not to the side or down. Everybody the other way. Everybody have your pin head up. And do some target shooting so that you convince yourself that you can get the tip of the pen right in the center of that circle. Okay. All right. Now, can you see the tip of your pen, Kent?
Yeah.
Okay. All right, now, what I want you to do, keep the pen up and turn it around and do the same thing now and target shoot again. And tell me what you see. It's inverted, that's right. You have to do a little ray tracing to figure out why that gets inverted, but it's a pinhole camera effect. And I want you to cover up your other eye. Cover up your other eye, and then take it away and watch what happens to the hole. Cover up your other eye again. Yeah, take it away.
That's for people who have equal eyes.
Okay, Kendra, do you see the change in size?
Yeah.
All right.
It's major.
Well, see, the eye that is exposed the most to the light is the one that governs the situation. And that opens and closes the iris of the eye to protect both eyes. And once you cover up that eye, then the other one allows a greater opening. But anyway, this can work pretty well. Okay, so the idea is to get some slide. I just happen to have this one, and you have a figure a little bit more to your slide. It's really a little bit better. I just need it better, but already see it's kind of blurred, so it's important to start out with a pretty good sharp focus. Okay, when you cover this up with a cube of glass, it causes the image to suddenly appear about 1/3 of the way up. And I want everybody in a minute, well, wait a minute, to come up and look at it. You can just, when you look at it, it just looks like it's kind of midway. Your object rises, in effect, and that destroys that relationship between the object distance and the image distance. from this lens, you've got an object distance, image distance that's just right for a sharp focus. So that's been changed when you change the location of your object. So you have to regain a sharp image, you've got to raise this about the same amount that your object. See, that regains a sharp image to regain the same object distance that you started with. So now it's a little bit fuzzy that way. Let me do it one more time. Start out with a pretty sharp image, some slide. Cover it up, it's a little fuzzy, and the object distance rises about 3/4 of an inch. The object rises, and so that changes your object distance. So you have to increase your object distance a similar amount to regain the sharp focus. And so that's called a shallow. Anyway, would you come forward and look at it, and you'll believe me more.
Everybody has to wonder what it would be like if you were to go to Jupiter and woo-wee, let's have a party. Wow!
Well, you gotta make a fool of yourself once.
Deliberately.
So you just do that for fun though, there's no...
Yeah, there is. Let me show you the physics. Our frequency, due to the fact that you're changing, the wavelength is fixed. That's the length of your voice box. That doesn't change. That determines that fundamental wavelength. But when you change the helium, you change the velocity of propagation by about a factor of 3. And so accordingly, the frequency has to increase by about a factor of 3. Lambda is fixed for the size of your voice box. And changing to helium increases the numerator by about a factor of 3. So accordingly, the frequency has to increase to get that higher pitch. Can I be here? We'll do this along about third week of June. Will you be here then? I don't know.
I'll be here, so I'll videotape it.
Okay. Well, you lie down with a bed of nails, and you put another bed on top, a smaller one on top, and you put a concrete block on that, and you have an assistant, sometimes a student. They're easy about students. And they hit, they hit the concrete block and call it a crack. And it leaves a little bit of an imprint on your chest, but it's gone by the next day. Okay.
Vandegraaff, it's got this red lead out there. Is that?
That's an opposite. That's like a ground. This is positive. I think this is positive.
I see. So that's the opposite.
That's the opposite.
You want to finish using that?
I believe so.
The camera, yeah.
Yeah. Thank you.
Yeah. Okay. All right. And let's see. I remember your electrostatic motor there, and then we need to. Okay, we'll find a gasket for this, and the optical rail. That's just that's for general things.
I got that, and I've never really gotten into that. I bought it thinking, well, this I ought to use, but they get a pretty good dose of lenses. The truth is, I ought to get with it and do more. But it's a nice bench.
Okay.
I just haven't really made use of it.
Okay. All right. Just on this shelf, I mean the obvious things, but this is this a mechanical?
This is a. I believe that is
a mechanical pendulum
it's a
or
centripetal force apparatus that used to be used in a laboratory, and I fact, it may still do.
So it spins around and you observe the...
Yeah, you observe the amount of stretch
Mhm.
versus speed of rotation, something like that.
Okay. What about, there's something that looks like a train up on the top? Is that just I mean, that's not a working thing, that's just to illustrate the piston?
I never really got it down to even step.
I see. Let's see. Anything else of...
Basically, this has been mechanics.
Right.
And then with electrostatic stuff over at that end. And then direct circuits and magnetism here.
On the shelf there's cylinders. What are these used for? Are these just rheostats?
These are the rheostats.
Just rheostats.
I use them on occasion. I wish I could have shown everybody my current balance. It shows the motion and
Oh
traction.
yeah, okay. Yeah,
You seen that one?
yeah, that works nicely actually. So.
And
It looks like somewhat just a magnetic coil there.
yeah, you sprinkle iron filings on that, and then they become aligned when you pass a current through the coil.
Yeah. Okay. Any of the things on the top shelf?
They've just been sitting there for years.
Okay. What about this? Is this?
That's another one I've never really used. So I don't even know what it's for. We need an experimentalist that, that has a real genuine interest in this kind of thing.
How about, let's see, the light bulbs I've seen, and it looks like a motor was that recently built?
This motor?
Yeah.
Yeah, John Fagan's built that one, and it uses the coil itself. You don't have a separent magnet. The current itself through the coil provides your magnetic field. So it's kind of interesting, right?
Okay. And any of these?
I used to use this to sit in the chair and turn and spray that carbon dioxide, and it'd make me go in a circle pretty fast, a rocket effect.
All right.
But I was always having to drive over to Oak Cliff and spend $35 to get it charged up every time I did the demonstration. And I just finally quit. Just too darn much work.
Okay. This is an odd looking.
Yeah. There's a demonstration I've seen that I've always wanted to do, connected with two. The whole setup is right here. Somebody ordered it before my time, I think, and they never did follow through. And you're able to show the radio waves on two transmission lines. That's what it is. And I've seen some years ago a demonstration of that. It was a darn good one, but I never did figure it out.
Okay. They're your standing wave tubes.
Yeah.
These metal ones are...
That's a good one. They did that one in our circus, and I wanted to show everybody this.
Yeah, so that's the same idea though?
Yeah, but a quarter of the way of the length, you have a little membrane. Yeah, this one, see that? There's a little membrane. What is that? Well, anyway, I don't have a membrane. I've got some of these in my cabinet. I need to get this one going, because it's a kind of a neat demonstration. These are called hooting tubes, and you put them over the Bunsen burner, and they give you a standing wave. But that's it. It's getting that. It's a little wire mesh that you want to insert a quarter length point, and getting it inserted, and it sometimes burns out, and a little headache there, but still it's a good demonstration.
Any idea if, I assume just the...
Been there a long time.
Just the
That'd be an interesting one to...
galvanometer, just
This one is a good centripetal acceleration problem. a demonstration that but it's hard to explain.
Mhm.
That's my problem with it. You light the candles and then you just give it a twirl like this,
Mhm.
and the class sees the flames lean in, and it's all kind of interesting, but it's hard to explain.
Mhm.
And I have a sort of a feeling for it, and you might do better.
Mhm.
But they do definitely see the flames lean in,
Mhm.
and if you could give a good explanation that doesn't snow them,
Mhm.
it's worth doing.
Mhm. Okay. Okay.
Of course, the solid state stuff has just sat there for years.
All right. Mhm.
Now, there's a microwave optics kit here that's a dandy
Mhm.
that has been bought and not used. I mean, everything's there, I think.
Mhm.
Just, which show your diffraction patterns and things with microwaves.
Mhm. So you need something, a microwave receiver to measure, pick it up, and. Mhm.
And this one I wish I could have done. I just did this one time last fall.
Mhm.
But you use the air hose and you get it going at a pretty high speed. You play Mary Had a Little Lamb
Oh, I
with
see.
your air hose.
I see.
And these things are on different frequencies depending on your radius.
Uh-huh.
You can't, because of the nature of the musical scale, if you have a couple of notes that are right, the others are going to be off. They're
Yeah.
flat or sharp.
Mhm.
So it's kind of disappointing because you can't really get the tune right.
Mhm. Mhm. I see. Those are just random light sources on the bottom?
I don't use them. So.
Mhm.
Kind of a problem to keep it all organized because different stages, people are always reluctant to throw things away.
Right. Mhm. And
I had a soap film demonstration. It's been a couple of years. It turned out to be all that great. I might get this one going. If I do, I'll show it to you.
okay. Mhm. Is this most of this stuff pretty much is storage over here?
Yeah, stuff that had been used in decades.
Mhm.
You know, I ought to mention to the class sometime, to the faculty.
Mhm.
And I use these extensively, in different slides. I mean, I just go through, every time I teach, I show them these slides.
Mhm.
But this set of slides is so old. So see how I had to put Scotch tape over these things?
Yeah.
They come apart.
Mhm.
And it's kind of, ever see that, how that one's come up?
Yeah.
Anyway, every time you go to use these, there are a few bad ones
Mhm.
that are sort of a pain. But other than that, I mean, they are just really good slides.
Mhm.
And I go through 4 or 5 of these every time I teach the course.
Mhm.
And if that slide projector is the one that's
Yeah.
supposed to be here,
Okay.
that would make that so much more convenient.
Yeah, I'll show it to you
For
because.
about a year, I've been going to the media center.
Oh,
with that
okay.
slide
Yeah.
projector.
Well, there actually, in addition to the one in my office, I remember there was one in here because I've used.
Oh,
Yeah,
we had 2.
Yeah. So we may still have lost one, but
Okay, maybe.
yeah.
Maybe.
Mhm.
So, it's all pretty self-evident. That's why I don't
Uh-huh.
think you need it on your tape.
Yeah. Okay. No, I appreciate that. So.
There's one that I started to do, easy to do, with the handheld, what do you call this? Can't think of the name of the car. The Tesla car, handheld Tesla car.
Oh, I see.
Anyway, it's kind of interesting to draw a vacuum and see how the pattern
Mhm.
of currents change as the density decreases.
Mhm.
And,
Mhm. I see. So you just run the Tesla coil to that, and then.
I hook up the vacuum
All
pump
right.
to this, shut that one off,
Mhm.
and just touch the Tesla coil of this.
Mhm.
And, you don't see anything at first, but after the vacuum begins to build,
Mhm.
then you start seeing the pattern.
Mhm.
And it's interesting.
Mhm. Okay. All right.
And the Wilson cloud chamber is a good one. That it's not so great for a big class, but if you got a small class, you show them those little alpha particles going through that alcohol vapor. You ever seen that?
Which one is that?
Let me show you this right here. You have to soak this all in alcohol, and then you go get a piece of dry ice from chemistry. You let it sit for about 15 minutes, and then you take this source of alpha particles and you stick it in the window. Oh, I didn't show that. Goodness.
Which one?
Well, there's one with a mercury arc lamp I wanted to show everybody. See the ultraviolet lines by means of a fluorescent board? I forgot to do that. But anyway, you use a lamp, like this lamp right here, to shine down, and you'll see these little vapor trails, the alpha particles, going off that little needle.
So you saturate it with alcohol and then cool it down, so it's sort of a super saturated.
You just set it on a chunk of dry ice. And after it's soaked for about 15 minutes. And stick this in there and shine a lamp on it. And you'll see these little vapor trails coming off.
Very nice.
And so for a small class, it's interesting for them to come up. They kind of have to stare to see those trails. They're pretty tiny.
Yeah.
So anyway.
Okay.